Hi. I wanted to record myself doing one of these past midterm ones. So this isn't really a walkthrough or me explaining how to do the problems. It's going to be me looking at a exam I've never seen before. Although, I've probably seen some of the problems in passing, but I've never explicitly done this exam. Um, yeah, so I'll try to do the problems, fresh and sort of explain what I'm thinking and how I arrive at the correct or the incorrect solution. And then at the end, I'll see how I did. Um, yeah, I think I've done one of these in the past for midterm two, and a lot of people like them. So I want to do one for midterm one. And yeah, I mean, hope it's helpful. So here we go. It is 5:24. So I'm gonna cut myself off at 6 uh 43. Cool. All right. We start with the what would Python display have a function. All right. What is the last line printed? Suggesting there's going to be multiple lines. So, um, all right, here we go. So if I do all right. So sorry, struggling a bit with my setup. Okay. So all right, so a global frame. Environment diagram isn't really needed here. It just helps me keep track of things because my brain struggles to keep track of too many things at once. So it's good to lay it out for me. So I have a mad function. Um, so that is going to be bound to a function object of mad that takes parameter max. This is the intrinsic signature of the function. And then we just print it. Okay, I really did not need to do that. But let's start here. So we evaluate the operator being print, and then I have to evaluate operand number one and then operand number two. Okay, so operand number one is mad print this thingy. Okay, so now we recursively apply the evaluation order. So I'm gonna evaluate the operator first, which just evaluates to the mad function. And I'm gonna evaluate the operand, which evaluates to the print function. And then I'm going to pass this, or now I'm gonna call the function. So we're going to open up a frame calling this intrinsic signature, mad max. In comes print for max. So this will just point to the print function, which is, probably somewhere global. Or I mean, this is just a built-in function, so I don't think we have to think too heavily about it. And then what's going to go on? We have a G that is bound to a lambda function that takes no parameters because there's nothing ahead of the colon. And it does this thing. And then we're going to return G. So RV return value is going to return this function. All right. So what have we just done? We have called this function, and this spat out this lambda function, whose parent is equal to frame one. So we have this lambda thing, and now they're saying, hey, can you call it for us? So let's call this lambda, which is going to kick us over here. And okay, here we go. So what are these parentheses for? I guess just for clarity. So we have a or expression. We're just gonna go left to right. So let's tackle this guy first. All right, so we're gonna print one. So we evaluate this print thing, and then the first thing that we're gonna get is this one that we print. This evaluates to none. None is a falsy. It's sort of a value, sort of an empty value, just like zero or an empty list is also falsy. So because it's falsy, or is going to keep looking for a true value, and two is true because it's not zero. So therefore, this whole thing evaluates to two. So now what we actually have is cross out this guy. We just have a two here. And now we have two or print three or four. So again, what does or do? Or is going to look for the first true phi value. And because two is already true phi, then this lambda function simply returns true, returns two, right? So yeah, we return two. Where are we? Okay, we're here. So calling this lambda gave us back a two. Okay, so this whole guy is just a two. Um, okay. But print has to, before I can actually print this two, remember that the order of operations is evaluate the operator and then the operands. So I have to go ahead and run through this through all of my operands. So I evaluate seven. Seven evaluates to seven. So I evaluated two out of my three operands. One more guy to go. It's going to be the print A. In evaluating print eight, I will actually get an eight, but then remember the print function itself returns none. All right, there we go. We've evaluated all three of our operands. So now I can finally apply the operator, and that's going to put everyone together on one line, giving us a 2, 7, none, I hope. Is that an option? Cool. Okay. So I'm assuming I'm right. The takeaway for these is I'm just running through applying rules, right? There's no real intuitive method I use to come up with something. It's just I'm running line by line, writing things out by hand to keep track of all the information, and then um, getting the output. You just kind of just have to become Python and apply the rules by one. Yeah, there's not too much to overthink for these. You just need to be super sharp with the rules, and that's indeed what we're testing you on. Which of these lines appears somewhere in the printed output? Okay, so I mean I had 1, 8, 2, 7, none. So what was the other one? 8. Hey. So, oh, whole lines. Okay. Start wondering if we needed 2 sevens, but whole lines appear somewhere. Okay. What order do 1, 6, 8 appear in the printed output? These numbers may appear as part of longer lines if number appears twice. So I do not have a 6 or an 8, so therefore I'm wrong. Thanks to this problem for kind of hinting that. Okay, I didn't do this. So I'm just looking at this original snippet, looking for a 6 somewhere. So the max of 5 and 6, this is going to be a 6. So okay. So sorry to be confusing. I've already made a mistake on the first page. Looking great for me. But fortunately enough, they made it real easy to tell that I made a mistake. So we just backtrack a little. Fortunately, the mistake I made is going to be pretty easy to backtrack to. So it's just here that I missed executing this line, which means okay. So at some point we call this mad print. This returns G, and then we call G. Okay, okay. But in calling mad, we were supposed to execute this. So before it spits out this lambda, and recall that this lambda produced all of these ones, we actually are going to print 6 first, okay? So first one's going to be 6. So these are going to be the output of calling, and then this is going to be the output from calling mad max. Okay. So it seems like we are going to have a 6. And what numbers do 1, 6, 8? So what order? 6, 1, 8. Okay. Environment diagram time. And again, this is also another very mechanical problem. There's nothing really to think about except to apply the rules and get through it. On my first midterm, I wasn't very good at the more maybe creative problems, the ones that required a little more thinking, the actual coding problems. I didn't get too many points on those, but I did spend enough time on the environment diagrams to get okay at them and get a lot of the points from the 1 and the 2. So I would really spend a lot of time studying these. They're going to make up a good portion of your exam. And if you're able to mechanically grind out these problems, then you give yourself a good base to do well on the exam. So yeah, they're painful. Definitely study them. So here's usually where I whip out a new sheet of paper and I start drawing. So this looks long. Okay. So they've done a lot for us. I always draw my own, no matter what. Okay. Global, we have x is 1, y is 2, and z is 3. I have a switch function, which is going to point at func, and then function's intrinsic name is switch of x with a parent is global because it was defined in the global frame. Python interpreter is going to see this defined. It's going to skip down here, define the next function, which point to a function with intrinsic name of which this is its function signature. Which one? Parent is equal to global. And then, all right, here we go. So we are going to, on line 17, call switch. And then, so now we go through our evaluation algorithm, right? What's step 1? Evaluate the operator. What does that mean? Python sees this word switch and it's going to search in our environment. Hey, what is switch? There we go. We found it. And it evaluates switch to function switch, which is obviously no shocker, but this is a process it has to do because maybe we renamed this function to which, and then the its name and its intrinsic name are no longer identical. Okay. So we call switch. So I'm going to do a frame 1. I'm going to copy and paste this intrinsic name down here. No thinking required, purely mechanical. Parent is equal to global. All right. I apologize. I'm not following the rules, right? The rules is to evaluate this and then evaluate this before we call it. Calling is opening the frame. So before you open up the frame, Python has to know who is calling and what is being called on. What are we calling on? X plus 1. I'm going to grab X from the current environment. So this is 2. So this means that we are passing in 2 for the formal parameter. So X gets 2. Let's jump into the function. This is going to have its own z. And then I'm going to say if X is equal to Y, what is Y? Python asks what is Y. it sees no y, but it's going to recursively backtrack up to its parent and find that y is 2 in the global frame. So it's going to say, is x, which is 2, equal to y, which is 2? Absolutely. So I'm going to jump in here, and we end up defining a new function, also called which, right? But this is where the need for the environment diagram shows, because it helps keep track of functions with, that are very convoluted and have identical names. So I have another which function. This is going to point to func which one. And what is going to differentiate this from this guy? Well, this guy was defined when we were from the context of the global frame, right? We defined it when we were running along over here. This which we defined it when we were executing over here from the context of frame one. So therefore, its parent is going to be frame one. Okay. So we went through this if, so I'm going to skip the else. I'm going to define a x, but we already have an x, so I'm going to wipe out the current one. X is equal to which of x? So here we go, and yet another function call. So I evaluate the operator, and that's going to, well, we see there are two whiches now, right? But because we start the search for which in the current frame, Python's going to find this one first. Okay, so the evaluating the operator comes out to the which function from frame one, whose parent is frame one, and we're going to also evaluate x. What is x? And yeah, I'm doing subtle things that violate how Python actually works, right? I shouldn't have just crossed out this x because we had not actually set that value yet. We're still in the process of evaluating this function. So this 2 still exists. So it's going to grab that 2 because, again, it's the closest x frame-wise. It's the x in the current frame. So this comes out to 2. So now that I've validated the operator and the operand, I can finally apply the operator on the operand. Applying the operator means calling the function, means opening up a frame. So finally comes the existence of frame 2. I'm going to copy and paste this intrinsic name, which one, whose parent is equal to frame 1. And then this 1. Every time you go in, you're going to start off by setting the formal parameters, and 1 is 2, like we figured out up here. Okay, so once I've done those mechanical steps, I'm going to actually run the function. So which function are we running? We're running this guy, right? The which one that was defined in frame 1. And when we call this function, all it wants to do is return x plus 1. Okay, so 1 is going to be the 2 because we passed in a 2. But now we have to figure out what x is. All right, so we are in frame 2, and Python's like, hey, what's x? All right, so we start looking in here. Do I see x? Absolutely not. I'm going to go to my parent, frame 1. Do I see an x? Oh, it's stat 2. So x is also 2. So the return value is just going to be 2 plus 2 equal to 4. So now the function has executed. We have a return value. We just got to think about who are we going to return that return value to? Well, who called? The caller was over here, right? So this whole guy produced 4, but we just kind of called it in a vacuum. I didn't do x is equal to this. I didn't print it. I'm not actually going to use the return value. So I'm just going to produce a 4 and no one's going to use it. So be it. So Python's just going to forget about this 4 because no one ever decided to use it. Oh, wait. No. We're on this line. Oh my God. Why would they do this? Why would they do this? To trick people like me, I guess. So this produced a 4. So now we're gonna hand this 4 over to X. So X gets bound to 4. So this 2 over here that I was so hurried to wipe away. Now we're actually gonna go ahead and do that. So instead of this being a 2, X is now 4. And don't tell us they're gonna make it call it again. Um, what awful people. So now we're gonna hand this 4 over, opening up another frame for which hey, so just because we call it twice, does that change the function that we were calling? Um, maybe, but in this case, no, because when Python tries to look for the variable which, um, the the binding that is closest is still um, the which that it finds over here. Okay. Um, oh, okay. Sorry. So we're back in frame 1 now. So it tries to find which, and it's going to find this which before it finds this which, right? So gonna open up a frame 3. Which one? These are identical, right? Because just because we called it twice, it doesn't change where the function was defined. And that's all this parent is saying. So 1 this time is going to be this 4 that I just set. And then it's going to add X. Well, now, before, remember, we grabbed the X, which was 2, but then we set it to 4. So now when we try to grab it, it has become 4. So it's going to return 8. Are we returning this to anyone? Nope. This produces an 8, but no one's there to receive our value. So that's it. We don't go on to the next line, line 13. Our function has ended. But any function that doesn't return anything explicitly will return none implicitly. So this function as a whole is going to return none. And then my function just returns. So I'm going to think about who am I handing this value back to? Before we go there, let me just finish off this frame. None. And then I'm going to say, okay, who asked for this value? So who called? So we were in the process of calling switch, right? Switch returned none. This was called over here. So this produced none. But again, no one's there to receive it. No one wants to print it. No one wants to set it. So, it's just going to get forgotten in time. Well. On to lines 18. Going to go here. X is equal to 5. Well, I just got done. I just exited out of frame 1, right? And that's going to return me to the frame that called me, which is global. So now I'm back in my global space. They're going to say X is equal to 5. So which X am I going to set? I'm going to set this at X because I am currently in the global frame. So this 1 is going to get wiped away. It's going to become a 5. I'm going to call which on Z. So here we go. We're going to call which again. And then from the context of the global frame, the which of closest proximity is actually going to be this one. So here we go, frame 4. Draw it over here. It's going to be which 1 parent is equal to illegible. Parent, it has to be global. And 1 is going to get set to whatever the value Z is. Again, I'm doing things out of order. So bad habits for me. Don't copy that exactly. Again, what should have happened is I evaluate this first, and I evaluate Z next. Z comes out to 3 because I'm in the global frame. And then do I apply the operator, which means calling the function, which means opening up the frame, right? I'm kind of doing it backwards and just opening up the frame because I'm not just because I'm teaching it poorly. So this should be the last part because when I open up the frame, I should already know what's coming in, and what's coming in is going to be that 3. So Now the which we're calling is actually this one. And it's going to return x times 1. From the context of frame 4, it's going to look for x. And some people here might make the mistake of looking back in frame 3, but you don't go up the frames, you go to your parent, which is going to skip us all over here. And so when I do x times 1, the first x I will find is going to be the 5 that we just set on line 18. So it's going to be 5 times 1, and 1 is 3, producing 15. So this produces 15. It's going to return it. All right. Now I'm going to go in and check my work against their template. So I have global, switch parent is equal to global, switch, which. All right, let's fill in the blanks. Blank A is in frame 1, what is X? That's going to be 4. In blank B, which is set to func which 1, whose parent is frame 1, because we just defined it within that frame. Blank C, frame 1 returns a none. Blank D, which frame 2 returns a 4. In E, frame 3 returns an 8. And F, the parent of frame 4, is global, because we were calling this one that was defined in the context of global. So F will be global. For G, 1 is going to be set to, in frame 4, 1 is 3. And then H is going to be 15. You should do so many environment diagrams that you start to love them, because you don't have to think. You just follow the rules. Hate thinking. It's awful. All right. So now I have to code, now I have to think. Really sucks. Let me check the time. What's the time? When's that? When do I have to stop? Cool. Final digit. Okay. So again, I'm treating this, or I'm doing problems I've never seen. So I'm just going to, like, it's gonna be train of thought. The other ones were more mechanical, so I was able to kind of explain as I go, just because I've been exposed to these concepts a lot. But now I'm gonna have to do some real thinking, so it's gonna be less coherent. Apologize. Implement final digit. Which takes a non-negative integer n. As long as n has more than 1 digit, replace n with the sum of the digits of n. Okay, so let's say n is a positive, non-negative, so it can be 0 too. As long as n has more than 1 digit, so that's 2, replace it with the sum of the digits. So this should be replaced with the sum, which is 3. This process repeats until n becomes a single digit number, which is returned. So in this case, I automatically have already become a single digit number. And I'm going to return that 3. So this was instead 1, 2, 3. So I'm going to, since it has more than 1 digit and it's non-negative, it wants us to replace it with the sum of the digits of n. So 1 plus 2 plus 3 is 6. Okay, not too interesting. Let's add a 4. That brings the sum to 10, and then I'm going to keep sort of squishing this number down, summing it together until it becomes 1. So kind of this iterative process that's going to crunch a number down until it becomes single digit. How does John keep coming up with cool problems for years and years? What a smart guy. All right. So let me just run through some of these to confirm my basic understanding. So we have a 3, 2, 1 that's just going to come out to a 6, and so we are done. 9 plus 8 becomes plus 8 plus 7 becomes a 24, but then I have to sum these digits to get the 6 and return the 6. And I don't feel like doing that. Cool. So this is saying while n is greater than or equal to 10. Okay, so this is saying while we're not single digit, and we're going to return n. So while we're not a single digit, do this. If we are a single digit, do this. All right. Take a break. Okay, so for these, I like to generally come up with a plan and then lean on their skeleton, see what kind of clues I can derive from these guys, and then form a solution. I'm able to do that with problems I can solve in my head. Sometimes the problems are really hard, and then I just kind of have to start over here, scrap together what clues I can find, and then find a solution. But I always try by seeing if my brain can conjure the idea first, um, because I think it helps me orient better and make sure I know what I'm thinking about. Um, okay, so while we're not a single digit number, what is the algorithm? So I see 3, 2, 1. I see that it's not single digit. That's what the while is for. So while the text multi-digit, and then if we are multi-digit, then we have to do is sum all the digits. So we've summed digits in homework or lab or whatever, right? What does that involve? That involves another loop, or that involves we have to. So if this loop through digits, right? That's the algorithm that hopefully we're familiar with, which is just while n have like a sum equals 0, and then I'm going to iteratively add on 1 digit at a time, right? It's just like for looping through a number, but we're not able to, so we have to use this some clever math tricks, right? So we grab the last digit and then we truncate it, grab the last digit and then we truncate it by 1 digit. So we're going to sum plus or equal the last digit being n mod 10. And then before we move on to the next iteration, I have to chop down that last digit so that on the next iteration, when I try to grab the last digit, it's going to be the second innermost digit from the right end. Right. So this gives us the sum. So if our original, okay, so replace OG with this new sum over here. And then loop. And then this part's going to go inside this if, right? So this is the iterative algorithm that's going to keep running until we're single digit, to which we can just return it. Nice. Okay. So I know this should be a while. While n. To make that more explicit, maybe they want n greater than 0. I don't know. S looks like it's going to be the sum to help us keep track of the current sum that we're accumulating. So we're going to start it at 0, and then we're going to loop through the digit. This sum is going to get incrementally, we're going to grow it incrementally. So it's going to be S, whatever the current sum is, I'm going to tack on the value of the last digit, which is N log 10 over here, right? And then I think this has to be the replacing step. Yeah, so I want to replace the original number. What is the original number? The original number is the number that came in, which is this N. And we're going to replace it with this sum. And then just as a quick sanity check, are we ever going to infinite loop? Does our algorithm come to some, will terminate? Well, I see that okay, so this loop builds sum up to be the sum of the digits, and then we swap out n with that number. And so on the next iteration of the outer while loop, it's going to check this new sum, and it's going to keep going until we are a single digit, and we're going to return it. Cool. Oh wait, while is this while enter s? S makes no sense because the first iteration wouldn't even run, right? If it was while s, then s is 0, can't run. C s plus mod 10 d n is equal to s. Okay, so that problem was an ideal case. I was able to just think of something in my head, use my own ideas, and then fill it in. It won't look like that so many of the times, and it's more going to be you're scrapping around for clues, you're doing process elimination. The moment I start struggling with a problem, I immediately process elimination, right? Any option I can cross out immediately improves your guessing game by a large margin. So you always want to be doing process elimination. I'm not going to do that for this one. Close enough. Implement close, which takes two non-negative integers m and n. It returns whether m can be changed into n by either inserting one digit, removing one digit, or changing one digit. Whoa. All right. If m and n are the same number, they are not close. Return whether m. So whether we can produce m starting with n and adding, removing, or changing one digit. Okay. So to me, what this seems like, so we're specifically going to be doing some manipulation on one digit. So if I have, so let m be 1, 2, 3, and n be 1, 3, 3, then we want to, so the number that we have permission to change is n. So we kind of have to do is form some algorithm to allow us to test each of these options. And our options are exercised over each digit. So that means I'm going to be iterating over n. I'm going to look at each digit. I'm going to say, hey, for each digit, you can do these three things. I can insert, remove, or change. Okay. And here I'm going to compare it to this one and see it's 3. So I shouldn't really do anything because I wouldn't want to kill the 3. So let's say this was 5. So I say if I add it, so in this position, adding a digit is not going to really help us, although we could maybe add a 3 to the end. The adding case is stumping me. Removing could help because it will get us to a 3. So, if remove, check if neighbor equals other equals m's digit. Or if I change. Well, if this is I honestly don't know. But if this was a 5, then I would obviously want to also change it to a 3, right? So if change, just change to other digit. But this add case, I don't really know. And this is kind of the point where I start to look at my options and try to see what hints I can get. So I'm going to look at the skeleton and think about what solution they're trying to impose on us. So given that there's 3, and then we're going to do this for each digit. So I'm going to need some while loop. So this while loop is going to get us through both numbers, irregardless of which one is longer. And then, yeah, I would have thought there'd be 3 ifs, but we just have 2 branches. Although this one does have an or, so maybe 1 branch, 2 branch, 3 branch. Check here that just 1 change is enough. Check here that just 1 change is enough. I don't know what that means. Okay, I don't immediately have a solution in my head. I'm gonna start seeing what they're feeding us. All multiple choice. Beautiful. Beautiful, beautiful. So A, if M is equal to N, M comma N equals something else. Okay. If M is less than N, swap them. Hmm. What is the purpose of swapping them? What more problems are there? 2-ish. Sorry, I'm probably not going to do the A plus. To save time, also my ego. Okay. Okay, I'm going to come back to this, but let's just think about A first. So this branch has less complexity, so it means we're likely dealing with a simpler case. The simplest case among these two is if like the digits we're comparing are the same, because then we don't need to add, remove, or change anything, is what I'm thinking in my head. So I would say like, hey, because this algorithm goes digit by digit, right? Like M equals N is tempting, I would say. Um, but like that doesn't really make sense. Like let's say I do if M is equal to N, then what am I going to set them to? Um, like I shouldn't need to set them. Here I would just return true, right? So it doesn't make sense to just check for equality between the 2 digits as a whole. Shouldn't be this guy. Or I can check if the remaining segment is equal. Maybe I'll keep that in the running. But then I think these asymmetric options don't really make sense. Because how would you determine which number, M or N, gets the asymmetry? Um, yeah, I can't really think of a reason to do this. They seem illogical to me. So to me, this follows along with our kind of digit by digit algorithm. This check, I'm not sure. Maybe it has some utility. These ones I'm suspicious of. I'll keep them in the running as I look at some other ones. Okay, B. So in the way I'm thinking about it up here, if I see 2 digits and they're equal, And all right, let's keep on going along. And now let's look at the 2 and the 3. And then the moment you find it that they're not equal, then that's when you want to jump into this branch and do some potentially complex thing there. So following that algorithm, I would want to truncate both. Um, it doesn't, I don't think we would ever want to set the whole numbers to just the last digit. That would kind of wipe away our number. Here we have two asymmetrical options, and here we have a swapping. Um, which like doesn't make too much sense because well, if we choose this option and then we just swap the digits, then the next loop they're also going to be equal, and they're just going to swap them, and then they're going to be equal. So this would produce an infinite loop if we ran with this. And then if we instead did this option, um, hmm, I don't immediately see why that would be useful. Okay, so C is where we go into the complex parts. So I know that E is going to have to be true or false, or maybe not actually. Okay, so good. Hmm. Hmm. Okay, so these are so awesome examples of closed numbers. Let's think about how we would solve them as a human. I have these guys, then we can do our looping algorithm. We check digit by digit. Are you equal? Cool. Let's move on to the next one. Are you equal? Cool. Let's move on to the next one. Then we get to this, we get to some difference. Um, but if there's a difference, we know that we can solve it just by changing it to the 7. And then we get to the next one, they're equal. So this is fine. So anytime we encountered some difference, we were actually able to skip it because I already know I can change it. I don't need to know what change that is. I just need to know that I'm able to make that change and get to the result that I want. If we try to run that algorithm here, 6654, I know I can change it, but now compared to 3 and 4, I know I can change it to make them equal. But now I run out of digits here. So if we're doing this iterative way, I have a 3 here and I have nothing here. Um, and because this is just a single digit, that's okay. Well, no, our algorithm would imply that we would be able to stick a number in the front. But the true answer is that the 5 should be something here. I'm confused. I need to think harder. And check here that just one changes in. What does that even mean? Check here that just one changes in. I will look at my options. Hmm. Huh. I mean, maybe iterating like this isn't the way to go. Okay. So let's think about what this portion does. Maybe that'll help us figure it out. So I have a m and an n. If m is less, then we're going to swap them. So this means that we always want the larger number as m. So m is the larger and n is the smaller. Hmm. But to solve this one, we can iterate. And at the end, when we see that there's just one digit left, we can return true because I know I can just add one whatever digit. Um, or I can add the digit to match these. But I'm not so sure my algorithm works when the insertion place is not the front. So let's try to construct an example to refute my own solution. So if instead of this, we have uh, okay, so they're always going to put the bigger number as m, and um, okay, so let's test this case. What if the number you want to add was actually here, right? And then here, what it's going to do is going to compare 6 and 5. See, they're different. So, okay, it's going to assume that we can change it. Um, then we look at the next digit. Um, we see that's a 5 in a form. So it's going to say, okay, we can change it. Um, I mean, but that would just return true for all numbers that are for any m that has one more digit than n. Wait, hold on. So does this return true for any two numbers that either have the same digits or have one less digit, one more less digit? Oh my God, I'm not doing well in this problem. Changing just one digit. Okay. So we cannot change multiple digits. So yeah, my algorithm would most certainly fail here. But to know that we might be able to get the answer by inserting something at the end, we should also compare this without the 6 with the current state of n. Because if these are equal, then I know I can just add a number at the end and we're good. But if they were not equal, then it wouldn't be possible because there would need to potentially be more numbers added or changed. So I think that could probably fulfill one of these, like if m being the larger number, um, if n mod 10 is equal to n, then I know that, hey, I can just add one number at the end of n and get us to where we want to be. Right? And that would imply that just one change is enough. Um, what is another case where just one change is enough? So we can add, we can also remove. So given we have two numbers like this, let's construct the case where, for example, um, I have 1, 4, 5, 6, 7, and 1, 4, 5, 6. Because, okay, so, and because again, they're always going to make the larger number n, right? So now I see that if um, the case in which removing one digit would just be enough is if this chunk is equal to n, because m has to be larger. Um, so yeah. Um, or um, wait, that came out to the same thing. Hold on. Okay, so this is a scenario where if n mod 10 is equal to this, then we're good. Now we also have the case of adding a digit, which would be and that would also just be if we remove this. Yeah, so you can either add or remove. Oh, because you can, okay, because adding a digit to n is symmetric to removing a digit from n. Okay. I know this will be one of them, seems like. Um, so that was one of the options here. Um, my brain's really getting work, so I'm gonna start here, assuming that is the correct answer. Um, what are some other scenarios where we just immediately know off the bat that we're good? If n is zero, that's not okay because if n is zero, then that means we run out of digits in n. There may be multiple digits in m. And we should only return true there if m only has one digit. And we can't enforce that condition. Um, if m minus n is less than 10, basically here I want to find some condition where they only differ by one digit, I would assume. Because if they only differ by one digit, then you can just or mm, no, that's not true. You wouldn't want to return true with this. Um, I mean, m equals n is tempting, but I'm assuming that would should be going here. Hmm. Well, if m is equal to n, then we would have had to go here in the first place. So I don't think that would be the most intelligent. This confuses me in what it's trying to do. Um, if the last digits are equal, that does not imply that we're just done. We have to check more digits. If the last two, that is no different. So we need something from there. Um, and in the very end, we have to so So these are the cases where just one change is enough. So this could very likely just be false. Um, if this captures all the possibilities where one change is enough. Um, if m is equal to if m is zero, n is zero. Um, can't be true. These maybe. Um, okay, so this should not be true because then we would just return false. Um, this is a possibility. These are possibilities. And this I don't really get. Why did I check this? It doesn't make sense why we wouldn't care about the last digit. I don't think we get any value doing that. Yeah, so I would assume it has to be one of these three. Uh, just construct more examples. 4, 6, 6. So they're saying if we kill uh, if we kill one digit from the m side and it's equal to n, um, so I guess this might be useful in like this case. Um, but it feels like we would already catch that down here. So they're saying if we kill one digit here and it's equal to n, then we would want to do something. Um, not sure if that does any good. Because we're saying it's like permissible to remove something, but it doesn't account for how many changes we've made. So if we go through multiple loops of this and end up removing multiple digits, we're able to detect that we remove multiple digits because we don't want that. Or maybe we remove a digit and then C, we can just detect that they're equal, because if they're equal, we just return true. It's a possibility. What about this case? So let's construct an example for 6. If n is equal to, yeah, I think this can like never really be true because m is larger. Um, right, this is possible because m is larger, so maybe if we chopped off one digit, we could still reach equality. Um, but if m, but yeah, since n is less, and if we kill a digit from n, it can never get it itself back up. Um, so yeah, so we can do this chopping here, and if we do that, then we will um, get it down to 416. And if we do that, then we can just check for equality. If they're equal, great. That means we can remove one digit and be fine. If we removed one digit and they're still not equal, then it's over. Uh, I would suggest trying different problems like moving around to keep your brain nimble. Because my brain is really stuck on this problem, but I don't want to make the video bad, so I'm gonna keep trying this problem. Um, yeah, but if we had done a deletion and they weren't equal, then we should just be returning false because that means we've already made our one edit and they still aren't equal. So I'm not sure about this. I mean, that leaves us with this guy. Um, so suppose we did this instead of this one. And then I would probably just chop it down. Um, and if we chop down one digit, we wouldn't want to return if they're equal. Because if they're equal, that's bad because that means the whole number was equal, which should actually return false. Um, so we've determined that the first two are equal. What is one way we can immediately tell that we can just return true? I have a 12 and a 13. Um, and then, oh, if the rest of the numbers are also equal, then I know that we just have to change the 2 or the 3 and we're done. Hmm. So like if we have 1, 2, 3, 4, 5, 1, 2, 3, 5, 5. We see that these are equal, so we move forward. We see that these are not equal, but if the rest of the numbers are equal, then I can just return true because that means we only have to change one of them. Damn, that took me a while. Uh, And um, if that's not true, then it might be the case that we can add or remove using this case and we chop down n because n is larger. So the other way around can possibly be true. And finally, at the end, if we never reach that, then it must be the case that it was false. But that doesn't look good because let's say we have two identical numbers, 1, 2, 3, and 1, 2, 3. Oh, that would just get stuck here since it's never not equal and then it'll return false. Okay, that's fine. I'm gonna move on. I have to in order to, to get a better score. But yeah, I'm just doing this in real time, so now everything could be perfect. I apologize. Implement shift, which takes a number k and one argument function f. It returns a one argument function g that takes a number x. for all numbers x, g of x is equal to f of x plus k. Return a function of x that returns f of x plus k. So we are writing a shifting function. So when you call shift, this returns a function. So that should immediately eliminate everyone here. What? No, wait, right? Oh, yeah, sorry, there's more lambdas. Okay. This is going to immediately eliminate everyone that is not a lambda. So we have to return a function. And this is a function of x. So good. We have all these x's. That returns f of x plus k. So I will return f of x plus k. I'm not going to overthink this one. Sorry, not that one. I should return f of x plus k. So this one. A lot of higher order function problems are just making sure you're very precisely following the rules. 643. I think these exams might be 2 hours. So I'm going to hope it's 2 hours. And then at the end, if it crosses 2 hours, then I'll just fail myself. Provide an alternate solution. This time your solution must call compose. And f may not be the operator of a call expression. You can't write f in your answer, so you may not call f. You may not write. Okay, return. I have a compose function. We're going to define a shift function. And it's going to return instead of lambda x, which is, I'm just going to rewrite this as a function to make it clear for my head. So instead of this, which is equal to this, it wants us to use compose, which returns a lambda of x, which solves this part, f of g of x. It must call compose. So compose returns a function. So I would probably just want to return a call to compose. I don't want to nest in another lambda because then I'll return a function that returns a function, right? So I'm going to return compose, which is going to give me a function. It's going to take two things. Doesn't say we can't use lambdas. And f may not be called. So the question is, where do we get our x from? So return a function that takes a single x. A function. And compose does that for us. So compose gives us a function that takes s. We just have to slot in the right f and the right g. Well, I know the thing that we have to do to the g is shift x by k. So my g should be like a function that shifts by k. And my f, do I have to do anything with that? Okay, so if we do this, what is the output that we get? If I do this, then I will return a lambda x that takes f, that calls f on g of some x. And then g will take that x and shift it by k. So it sounds like you're good. Yeah, so what is, so f sounds like just the f that is the like initial kind of function. And then our job is just to shift some input x by k. So I'm going to slot in the f unchanged. That is the function that will actually be called. And then using g, I will take advantage of g to do the shifting operation and manipulate x. So then I know that g simply has to be some function that shifts x by k, hopefully. Implement sum range, uh, which takes positive numbers p and q with p less than or equal to q, as well as a one argument function term. It returns a sum of the return values of term called on each consecutive integer, starting with p and ending with q. I have no idea what that means. On each consecutive integer starting, assume shift is implemented correctly. So we have to use shift. Sum the first n terms of a sequence, term one plus term two plus term of n. Summation of 5 is going to be what is 5? What is the point of 5? Implement, oh, so we're doing this. Sum range takes p and a q, p is less than q, and a one argument function. Since the sum of the return values, so we're going to call term on all of the numbers between p and q. You may call shift summation and compose. Assume shift is implemented correctly. It wants us to use the summation function. So summation, what is n? Summation of 5 goes from 1 to 5. While k is less than n, so k will always start from 1. Okay, so summation is a function that returns a summation of term of 1 plus term of 2 plus term of 3 plus term of n. We want term of p plus 1, and we have shift summation and compose. So I think they're setting up nicely to just shift the result of summation by p. So that is to say, summation necessarily starts summing, and by summing I mean summing together term called on a number. Um, it yeah. Um, but sum range doesn't necessarily go from 1 to n, it goes from p to q. Could start at 4, go to 5. So that means this has to go from 1 to n, this has to go from da 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 to da 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 da. So what we should do is we have to align them with a shift. Okay. So we have to shift. We have to find an amount and then call a function. So the function that's going to do the summing for us is just summation. And then we're going to shift summation by some mathematics. Okay. So we have some arbitrary p to q. Let's just do this, right? Let's say we have a 1 to x, and then we have 4 to 7. What do we need to do? We need to augment each of these by +3, +3, +3, and then x has to be like the length of this. So this has 4, 5, 6, 7. So this has length 4. So x has to be like 1, 2, 3, 4, and we add 3 to make that adjustment. So it's going to be the length of this being 7 minus 4 plus 1. Um, and then oh no, we just shift it by the difference. Mm, yeah, I mean, so this should probably be the length, which has to be this. Um, and that is B. So this is the length. We want to shift by the length. So we could also use compose here. Hmm. All right. Now let's say we work this example. This have length of a 2, and then it's just squaring. Um, and then what we want to do is, I think what needs to happen is we need to shift the term function. We can't just shift the whole summation function. Because shift, yeah, so it only shifts a single thing. So what we actually need to do is we need to shift term. Okay. Um, so this is going to have to be summation. It's by the length, but we have to shift term by the difference between the start points being p minus 1. Uh, um, okay. I will now check how much time I get on midterms. Um, maybe in some miraculous world we get 2 hours in which I can spend some more time. Uh, oh, we do get 2 hours. Okay, so I kind of rushed it, but that was 90 minutes. Okay, yeah, I would have felt bad ending the video there because I don't think I maybe talked through the last couple ones well, but I tried my best. Okay, I will spend a little more time, or I think, hmm, I mean, I did what I said I would do, which was just do the exam and talk about what I'm thinking. I'm thinking of some problems deserve a little more justice, because um, I do want to make this as helpful as I can. Um, so I think this one I didn't say much, but that's also because wasn't thinking much. It was just kind of translating this equation to fulfill into code. I promise you, I didn't think any more than the things I said out loud. Um, so return a function, so cross out the non-functions.
and we just return x plus k. An alternate solution, I kind of just played around with the different puzzle pieces. I know that f isn't really supposed to change because that's just sort of the ultimate thing that I'm going to apply. Um, but then this g, so then like f is at the outside, right? So um, the f that they pass in, we shouldn't make any modifications to that. That is just getting called on the final result. Um, so this g, which has greater proximity to the x, which we're just going to work on x first, is probably responsible for doing that shifting thing by the k. So here we're going to define, yeah, um, or as opposed to if we let's see what else. Hmm, like could this have been a lambda? Like this could be like a lambda x f. Well, I can't call it. Let's say if we swap these or something. Yeah, that just doesn't make sense because we would call it first and then shift it, but we need to shift then call. So it's because of the ordering that how the solution came up. This one, I don't think I did too much planning. I did just kind of try to solve it because I thought at least that I was running out of time. Um, but yeah, this was not a good one for me. First of all, I think the first one I put was shift, which is just wrong because shift returns a function and this returns a number. So immediately I made a mistake. You should always be mentally checking your return values. So this actually could not be shift or compose, which both return functions, right? Um, so right off the bat, I should have crossed these out and realized it was summation. Term makes no sense because we want summation over many terms. So that was a super simple one that I fluffed. This one, I mean, yeah, this one I was doing a lot of, I was trying to do the math here, but then I saw that these are all just length formulas, and I know that this is the proper length formula, right? Like the number of things between x to y is y minus x plus one. So I felt like it could only possibly be that one because that's the correct formula. But yeah, I think this one was just kind of this is really a math problem. So I think going through a example, because I like to work in concrete things because my brain is slow with super abstract things. So I like to make it concrete. And I think that was really helpful. This example, just coming up with, all right, if I have a 1 to x range and I have some arbitrary p to q range, like 7 to 100, what has to happen to perform this alignment? Well, first of all, I have to shift the 1 over by plus 6. I'll have to shift everyone over by plus 6. So that becomes my k being p minus 1. Um, and then what does this x has to be? This x has to be, this has to go as far as the distance between here and here, which is just there. Um, yeah, I should probably spend more time talking about this one, but it hurts my brain a lot. Um, run through an example. I'll run through a test. So yeah, if I have the luxury of time, I really don't. The first time I think throughout 61, I've never had time to check my exams. Just because again, this is me doing problems after like 4 semesters of teaching this, and I still struggle this much. Like it's just imagine how much I struggled when I actually took it the first time. Um, so let's see if our code works. Um, by the way, I have 2 hours being 150, and before I was giving myself 1 minute 20, so I have 30 more minutes after 6:40, so I should end myself at 7:13. Okay. Um, Let's see if our code works. Return C is if or and return false. All right. Does it return false for 5 and 5? So we come in 5 and 5 swap while M or N. We enter the loop. We see that the last digits are equal, so now we are 0 or 0. So we return false. Let's try on these two. We come in, we see that the 6 are equal, so we chop it down. Then we see that the 5 are equal, so we chop it down, and we have a 37 and a 34. Then we enter here. We see that 37 mod 10 being 3 and 34 mod 10 being 3 are equal, which implies that since the rest of our numbers are equal, we can make a singular change to here and get it right. So this is going to return true, just like we want. Let's work through this guy. So truncate, truncate. We see that these are, no, this is going to compare 34 and 3, not equal. So we're going to jump into this one, in which case we cut off the 5 and we compare it to n and we see that 34 is equal to 34. All right, so this is going to test the change case, and this is going to test the add/remove possibility. 3, 4, 6 and 3, 4, 5, 6. Oh, okay, so this is going to first swap them. No, these are the same because this is going to swap them because of the, it's going to orient the bigger number at the start. And then this equal. And in here it's going to look at the 4, compare it with 0. No bueno. And then it's going to chop off the 5. Whoa. Chop off the 5. Wait. Oh, wait, no. 6, 6, chop, chop. And then we just have a 4. And then this is going to say, hey, is 4 mod 10 equal to 0 mod 10? Or 4 div, which is true, I guess. So it returns true. It works for these guys. So I'm going to call it a day and go take a break. This stuff hurts my head. But yeah, I'll check it. It's very likely I could have gotten everything wrong. But yeah, I'm sorry if the way I solved this one wasn't the most satisfying. Um, but maybe it will show that like you don't like people don't come out of a problem and just know I am 100% correct. It is a lot of heuristics and guesses, taking clues. So yeah, sometimes problem solving looks like that and it's just a linear path. Um, yeah, I'll check my work and I'll leave any corrections in a comment in the video. Thank you.